talk short as well. First of all, I want to thank Mr. Prasad, Mr. Talukdar for being here. I'm honored to be the only non-Trinidadian speaker here, and second, for the great introduction to what I'm going to talk about, because both geochemistry you have talked about, I will try to include, not everything, but I try to include in modeling, which I have done and which we're doing in South America mainly. So talking about South America, where we are right now at this moment, is about here, but of course, you know, the source rock deposition 90 million years ago, more or less, Turonians, Cinnamonian Turonian, was a rich, nice, high sea level area where we can expect source rocks to be deposited, and mainly I will talk about the unconventional source rocks, shale plays, so shale oil, shale gas, not the oil shales, but the mature stuff, and gas hydrates. So let's look at first a vision which I got from Mr. Prasad on understanding geochemistry and especially the petroleum system. So the application of the geochemistry, trying to map petroleum systems, the single most important key to successful exploration. And worldwide, Trinidad and Tobago is no exception. I would say it's even a bigger challenge here because of your unique tectonic history. And there are very few areas in the world where you have so much strike-slip movement as here, in terms of the deposition of the source rock here and the position, the current position of the basin right now. So, thanks for the vision. I will share it. A little bit about myself, because you haven't known me until now, so I would like to give a very short introduction about myself. I was born in Holland, hence my pretty challenging last name. I was born at the beach. Already at this age I was intrigued by geology at the beach there. So I'm a geologist, I'm not a geochemist, I'm a geologist. And I try to move a bit in your world, but it's still challenging. So thanks for the great talk, so I can learn a bit as well. And then I studied in Utrecht University in the center of Holland in Madrid. Did my thesis at Shell, doing something completely different from geochemistry. 3D seismic, fault and fracture tracking in the carbonate field Oman, the biggest field of Oman. Then started working for Wintershall, worked in Shell again, teaching a lot, basin analysis and field geology mainly. Then started in Germany, in Aachen, where he developed the software Petroleum, which is using the geochemistry and applying it for modeling. Worked 3 years there, and then in 2012 I started in Colombia for Latin America. So I'm working for Latin America, and just as of this week I'm working for South America. So Mexico is no longer a part of my area, internal research. So let's look at some important concepts about shale plays. So shale plays, that includes shale oil, shale gas, and all the different components in between. What are the important concepts of shale plays? Looking at two main factors, the geochemistry and the geomechanics. So first we want to know how rich are the hydrocarbon resources, and then we want to know how to produce them. So can you frack the rock? Are there actually fractures already present in the rock? And the geochemistry important is first how much organic material is there deposited and how much is preserved. That depends mainly, you see here an image, and it's hard to see the curves, but what you can see is that the curves differ in terms of the depth and position in the basin. So the basin geometry at time of deposition is key to understand how the distribution of TOC values and thus the richness of your hydrocarbons will be. And is the preservation of organic matter. If you have basins like this with a sill and a deep anoxic basin, you have good preservation. You have basins like where you have upwelling areas, you can have good preservation. Also have oxidized material. Second important point is organic porosity. Organic porosity is porosity that exists because of the maturation of the keratin, maturation of the organic matter, showing or creating extra new porosity in your shale clay. Then, what you want to know is how much is there in two different phases: in a free phase, free hydrocarbons, and in an absorbed phase. For that we have an analysis called Langmuir, and this curve is coming from laboratory analysis, showing a maximum volume of absorption, the Langmuir volume, and a pressure which is at half of this volume. Curve touches there, and these parameters we use as input for our modeling, trying to map out how the behavior is, absorption behavior of the hydrocarbons. Going to the other part, which is a little bit on the side of this congress, I would say, but it's important, and that's the geomechanics. So how brittle is the rock, how easy is it to frac, or how many fractures do you already have in the rock. So these two factors are important for successful exploration of shale clay. We have done quite some work already for different shale plays, mainly in the US, also in other countries like Algeria, and we are working in Colombia as well. We're working with Ecopetrol on building a model for the La Luna formation for shale plays. So different ones: the Bakken Shale, Eagle Ford, Haynesville, shales here in the south central part of the US, and an example I will touch later is the Sugar Formation in Alaska. This model is showing that Sugar Formation, and this video is produced using our software on the north slope of Alaska. It's based on all these seismic lines, 2D, 3D, well data, and in collaboration with USGS. Last year, our famous geochemist working for us, Ken Peters, was here, and he has been involved in the modeling of this basin from the beginning on, and keeps on working on it. So what we will see is first the deposition of facies, different facies, then we will see the generation and then the migration, and especially the impact of tectonics on the migration scenario. So right now we are in the Permo-Triassic, Permian-Triassic ages, and what you will see later on is more detailed facies analysis at the reservoir and shallower source rock intervals. This model has been worked on already for 9 years with USGS, Stanford University. It's calibrated with well data, with geochemistry data, with Sarah kinetics, with chromatograph data. So now we're entering the Cretaceous here, and you see there are more detailed phases coming in the model. And especially at this age, you see there's a huge delta coming in from the western side to the east. You see this delta coming in, burying the source rocks deeper down below, and you will see the effect on the generation of hydrocarbons area. Also, you see the different uplift and new burial scenarios coming in, like here, this part. Then in the northeastern part, you see new burial, new uplift, creating new kitchen areas for hydrocarbons. And that produces the mixing mixing we saw in the nice diagrams before, both oils and gases. This is one of the source rocks, shoe lake formation, and it is a target area for shale plays. So at this age, remember the delta coming in, you will see the effect on the source rock maturing from the south to the north, creating hydrocarbon migration northward along the Alaska North Slope. So at this moment, 97 million years ago, something interesting happened in the basin. We're looking at an accumulation here in the center. This accumulation, something happened when just at the top of this, a meteorite impacted. And right now, all these gas fields, they are reported around the crater. The crater is forming the seal of gas fields in the area. It's published, it's proven, as long as you can speak of provability, it's proven. But here you see the effect of different kitchen areas creating the migration patterns for the accumulations in the Alaska North Slope with the famous Prudhoe Bay field here as giant hydrocarbon accumulation. And these different pulses have been confirmed, calibrated with geochemical data from these fields with different components, where they're coming from, APIs, GORs, and so on. This model actually was acquired by one of our clients, and what he's done is exploring for shale oil. And as you can imagine, Alaska, pretty harsh conditions. 5 months per year you can drill, and so you need to be quite sure to find shale oil and not shale gas or any other product that's not economical. So using our model, explaining the mix of oils proved successful in predicting the liquids, the liquid fairways in the area. Then we will go to a other model which I built. It's a conceptual model. It's not real. And that's why it's called the Mariposa Basin. I guess your Spanish is good enough to understand where it comes from or what it means. And it's a conceptual model on 2 different shale plays. The Vaca Viva and Las Pimientas formations in this basin. Let's look at the basin in a little bit more detail. It's all based on public data. And this is the stratigraphy with 2 different shale plays there, Vaca Viva and Las Pimientas formation. And maybe this will show why the name of the basin is Mariposa Basin, right? Using this input data and identifying these source rocks at the age of deposition, Jurassic, lower Jurassic, and upper Jurassic. I built a simple facies model, which may not be real, and probably is not real for this basin, but it is to show you the differences in lithologies, different lithological mixtures, like the diagram that were shown this morning with these triangular diagrams of siliciclastic, carbonatic, and argillaceous material, and also different source rock properties. So different keratin types, different HI values assigned to the basin model to show different effects later on. So here you see an example of the output of the modeling, which shows porosity. And this porosity is total porosity, and it shows areas where you have high porosity, and it's related, as you can see here, to the TOC values in the basin. So the TOC quantity creates organic porosity. Organic porosity apparently in this scenario is important. So the TUC mapping, TUC variation will tell you a lot about how your porosity in the reservoir will be. In the compaction history, the maturity, so the measured TUC versus the original TUC, and the tectonic history uplift. Why is that? Because you need overpressure areas in the shale plates. For a couple of reasons, mainly because to maintain the porosity, you have non-overpressured areas, you will get convection, you will lose your porosity. So you need enough overpressures to maintain your porosity in the shale plate reservoir. So important factor is the analysis of the paleogeography, which in this example here can be an indication for the original TUC variation in the basin. So it can help you identifying areas of higher porosity. This is for the Bacaviva shallower source rock. We go to the Las Pimientas deeper one. Also, we have here an example of the total porosity, and you can see here the different phases have an impact on the porosity, the organic porosity, and the matrix porosity. So you have different lithologies, different compaction histories. So the lithology and the Jaron type, which is also changing over the basin, are the most important factors in the analysis of the total porosity at the end. So the analysis of organofacious, lithological factors, plus the TUC and geochemical factors. This is an example of one of the outputs, and you can see here a plot where different phases are shown with the absorption characteristics. So the mass, absorption masses through geologic time. And what you can see here is that this is one of the phases which is absorbing a lot of hydrocarbons. Why is that? It is a more type 2, type 3 kind of keratin. So organofacious is affecting the absorption. Type 3 keratin generally absorbs more oil and gas than type 2 than type 1. And what you can see here, this keratin type 3, this area, you see, in time, there was a moment where you have a drop in absorption mass, which means something going on, and it is because there are no overpressures or less overpressures in these zones, while in these zones you still have overpressures. So if you don't have these overpressures and you either uplift or you bury your sediments more, your Langmuir parameters, remember this curve, pressure and volume, they will change, and the amount of absorbed hydrocarbons will drop in this area. Looking at the geomechanics, so what you see here is an overlay property of a deviatoric stresses. Deviatoric stress is a measure to show the extent of the Moore circle in geomechanics. And what you can see here, there's a line. It's an example line. It's not the real failure line of the lithology. But you can see you can use this to predict if the rock is fractured or not. Of course, it needs to be calibrated with real data. So all your wells will help to calibrate our models, but it is a way of predicting fractures or the absence of fractures, which may be even better for shale play because you can fract artificial. The main value lies in what was mentioned before, integration. I mean, we can look at every data point in its own, but full integration of all the data that is what makes the exploration successful or not successful. So, summarizing different outputs and different elements of the petroleum system: charge, reservoir, seal, frackability, producibility, and you may include different factors like environmental factors in the evaluation of the complete system. This process is called plate chance mapping, and what is possible is you can analyze block by block, prospect by prospect. So, let's look at some exploration, because in the end that's why we're all here, right? We want to find some hydrocarbons. So this is an example of the output of this calculation using the output of the petroleum systems modeling and ranking of blocks based on this analysis. And of course it's possible to vary your parameters, look for different scenarios, different interpretations, and change your exploration scenario based on that. This is for one play and one product and one phase. So it's the Tobago-Shale source rock, it's shale oil, and it's in the free phase. So per phase and per product, per place, you can analyze things. Then looking at the other source rock, the deeper one, this is the ranking of blocks, chance of success of blocks for all of the phases, so either in the free phase or in the adsorbed phase. And in this case, it's looking at shale gas, different product, different rock, and all phases. Then I would like to talk a little bit about unconventionals here, which you must know much more about than I do, but just from a modeling point of view and our experience on especially gas hydrates on the left shortly. Looking at the rock 90 million years ago, when Africa was still quite close by. Looking at potential first for shale plays. And this is the information I got from the summary, so please correct me if I'm wrong, because I don't know much about the basin here. Yeah. So, I heard about 3 source rock formations: Mariposa, Hydrate, and Gstt. Is that about right? Yeah. Type 2, type 2-3 kerogens. Deep marine to marine with terrigenous input. High organic richness, which is favorable for any hydrocarbon exploration, but especially for shale plays. And they can be highly mature, or as we heard this morning, in the 0.75, 0.95 range.
Over mature, which is over mature.
I think all you until now you are talking about shale gas.
Shale gas or shale oil?
Shale gas. Because the absorption desorption is also for shale gas.
It is defined for shale gas, but it also applies to shale oil.
Well, we can, but you see, mostly it is a concern. Many people thought that, well, absorbed gas will be really high to, fracture it and it will come out. No?
Yeah.
From dissolve. Oil, what are the experiments? When was this card is used in oil? Well, I don't see much literature about oil.
What I understand is that the curve is defined for methane, only methane, other gases,
Right.
and then the curve can be applied to heavier components with a correction factor.
But does it, is it important in the sense that oil, polar compounds will be absorbing, and what will come out is the saturation of metals. I don't know, I have not seen any literature yet which is discussing the concerns about oil absorption, except in some early research done by some shallow where they were talking about migration exposure.
Yeah.
I don't know. And highly mature obviously applies to gas, not to.
Yeah, sure, of course. And then the question, of course, is how is the extent in onshore area? Because if we're looking at the offshore, then shale gas, oil and shale gas is probably a bit too uneconomic. And of course, driving around on the island, I see it's pretty densely populated, like my own country as well. So the environmental impact might be a very big issue to assess these types of unconventional. Then let's look at another type of unconventional, which is gas hydrates. This is an image from Der Spiegel, German magazine, which shows the potential of fossil fuel reserves. Of course, it's highly questionable how much this would be, because we need a detailed analysis which doesn't exist until now. But what we have is this burning ice. This ice is formed in shallow, unconsolidated, low consolidated sediments, and it is stable at certain conditions in the sediments. Along the coasts of most of the continents, and also in the permafrost areas in Alaska and Siberia. There have been already some tests and production tests, and especially here in Japan, a test has been done using CO2 to inject to produce methane. So CO2 was injected and methane came out and produced. How did that happen? Looking in here, you see there is methane inside water, or water structures keep methane in there. So what's done is that the CO2 is replacing the methane, reducing the methane, and the CO2 is stored, which is good for two reasons. One, for production, but the other one, especially in the permafrost areas, the risk is this melts, this ice, and then the methane is set free uncontrolled. Methane has a 4 times stronger greenhouse gas than CO2. Might be uncontrollable when this is released in large quantities, especially in Siberia, where you have huge areas of these hydrates. So where do these hydrates form? There's a so-called gas hydrate stability zone, which is based on temperature and pressure. Low temperature and relatively high pressure zones. So that's why they form in these deep marine areas and in permafrost areas. How do they form? So these water molecules that are here in the sediments are filled with either thermogenic gas, methane coming from deeper below via different processes that I couldn't explain what you did this morning, or locally biogenic gas, methane. Then, at the base of these gas hydrates, you will find evidence, or you can find evidence in seismic, which is called bottom simulating reflectors. And these have been mapped and calibrated with, indeed, the position of these gas hydrates. Let me show you one example of this, going back to our famous Alaska North Slope model. Here you see the Shoe Lake Formation, the Permian, or the Triassic Formation we just saw in the video, but we are now focusing on the shallower area. This is the situation of the Basin model at 1 million years ago, 1.0 million years ago. which is quite recent. And you see there's a very small part where hydrate and water is stable. Green is hydrate and ice. So, going forward in time, 500 million years ago, this area is growing and other areas are forming as well. Mainly hydrate and water. Then, entering more recent times, you see that there are also regions where ice and hydrates are stable. These stability zones are based on temperature and pressure, and in Alaska, mainly related to the ice ages, glacials and interglacials, forming the stability zone and forming these methane hydrates. See, resolution of the modeling is quite fine, 20,000 years here modeled, and the area is growing until a moment where it's not stable anymore, either because of temperature or because of pressure, it's shrinking again. So it's a constant interplay between these parameters. Also, the input of methane. Looking at the situation today, here in Alaska, ConocoPhillips has produced these methane hydrates, and they have done tests, production tests, which flowed successfully. And what you can see in the modeling is biomethane. With the modeling, it's possible to trace different hydrocarbon sources, either biogenic or thermogenic, because, and mapping the area of highest richness of gas hydrates. Not only in the unconventional ones, but also in the conventional ones, which we saw in the video, showing the contribution of methane and different black oils coming from different source rocks. Source rock tracking contribution of different source rocks with information about masses, volumes, API, revenues, and so on. And a small, in this case, small contribution of biomethane in this explanation. So thank you very much. Difficult questions.
What's happening is the caterers are waiting for us downstairs.